Praveena from Group 320. I am going to explain about the non-equilibrium and thermodynamics in biology. In this one, my topic is in 9.6, the coupling of chemical reactions to transport of matter. First, we start about the coupling of chemical reactions to the transport of matter, especially across biological membranes. It is essential in the understanding cellular process. In cells, chemical reactions drive the movement of various chemicals, like chemical reactions across the membranes in specific directions, like facilitating the cellular functions and homeostasis. In this one, two couplings are there: direct and indirect coupling. First, the direct coupling. The molecules might move along spherical like pathways in the membrane, which could change the reactions depending on which direction molecules enter or exit. In indirect coupling, even if reactions are always linked to transport, they can still interact indirectly in steady state like conditions. Everything in the cell becomes interconnected, so the changes in one might affect the another, even if they are not directly connected. And next about the indirect is completed, and then directional transport across membrane. Chemical reactions within cells are often coupled with the transport of molecules, both and across membranes. This transport is involved, meaning is vectorial, meaning it has both magnitude and direction, unlike the state of chemical reactions, which is scalar. Scalar means the magnitude only. The biological membranes are made up of the chiral molecules and are anisotropic. Anisotropic means having different properties in different directions. Due to their structure, biological membranes lack symmetry. This characteristic, along with their chiral properties, enables a type of direct coupling between the chemical reactions and molecular transport that would otherwise not occur in symmetrical or isotropic systems. The Curie principle suggests that the direct coupling of scalar and vector process isn't possible in isotropic symmetry. However, the anisotropic and chiral nature of biological membranes permits such coupling. This coupling mechanics is crucial in cellular function because it always allows for controlled transport for ions, nutrients. In this equations, it describes the expressions for the flux of a component in a system by integrating related equations like that it cannot transport or it cannot produce chemical potentials. And this, in the ending of the topic, I would like to tell about this some summary like topic means the organisms and the chemical machines that operate as a result of chemical reactions and transport of matter between the cell and the surrounding medium. And it also inside the cell, this transport occurs in a certain defined direction perpendicular to the cellular and intracellular membranes. The flux of a matter is a vector. At the same time, the rate of chemical reactions is a scalar, and it is direct coupling of scalar and vector processing is impossible in the isotropic system by virtue of the Curie principles, nor it is possible in anisotropic systems having a center of symmetry. Biological system in which chemical reactions are of symmetry and biological system in which chemical reactions coupled in diffusion are however made of chiral molecules which have neither a plane nor a center for symmetry. Biological membranes are anisotropic. In such systems, direct coupling is in principle possible. That vectorial coefficient might be or maybe a different from zero. No theory of direct coupling between chemical reactions and diffusion in membrane has been worked out so far. One can visualize, for example, the transport of some reactions participates along the screw channel and diffusion in membranes. In biological membranes are anisotropic. In such system, direct coupling is principal. And then no theory of direct coupling between chiral reactions and diffusion in membrane has been worked out so far. We already talked about. And then one can visualize, for example, the transport of some reactions participants along the screw channel and the centers are located. Then of course the reaction will be different for substances supplied from the opposite ends of the channel. The same result is obtained by considering a symmetrical channel in which asymmetric means chiral reaction centers are regularly arranged. There is, however, no ground so far stating that these effects are considerable. And then the nutrients and signaling molecules across membrane. In this one, if you talk about this equation, this system of equation captures the idea that the transport of a substance across a membrane, it can be influenced by both in own chemical reactions and by the other substance like Q that may be respond to changing environment created by those reactions. And then if you talk about this next equation, in this equation we obtain like this, and this equation shows how each part of the system like A to F and transport of Q needs to be in sync to maintain the stable condition. This equation shows the concentration of Q on either side of the boundary will increase or decrease depending on the drive created by the reaction. With higher temperature, reaction forces increases its effect. And then this equations it continuously condition for its component is, it shows next equation it indirect coupling in the Kachalske and other the generalized force is the chemical potential gradient and chemical reaction takes place in this one equation. This equation tells about the steady state system. The concentration of substance remains stable. This balance means that the transport and reaction rates are matched, and when applied to the function, the precipitation function, it gives a simplified expression, means showing that energy lost in maintaining this steady balance, and it maintains the stable balance. This equation shows the and it follows the last equation. It follows that this equation and tells about this equation represent the calculation of total energy dissipation during a one-dimensional flow of substances along the x-axis by integrating over the distance from the O to alpha. Later, next equation tells about this. Provide a framework for understanding how the affinities of chemical reactions at the boundaries of a membrane influence the transport of substances across the membrane. And this equation tells about an isotropic system. The transport properties do not include of diagonal coefficients due to symmetry. And the next equation tells about the relation between the local and microscopic coefficients. It's decimal by applying a differential operation to the chemical potential.